Now let's apply the efficient encoding transform to the case of encoding binocular inputs. This topic is covered by this section of the textbook. First, we briefly record a general solution for encoding Gaussian input signals. The encoding transform K has the following three conceptual steps of signal processing. First, it decorrelates the inputs through a coordinate rotation, which is the principal component decomposition. Second, it applies a gain or sensitivity factor, GK, to each of the decorrelated components. Thirdly, it mixes these gain-controlled components through another coordinate transform. These steps combined together gives the optimal encoding K. While this K is a mathematically derived solution, we can use it as a recipe for building the efficient encoding transform. We will show how this is done for binocular visual input signals. We consider inputs from the two eyes. Here I show the retina images to the left eye and to the right eye. The input signals are transmitted from the retina to the visual cortex. Here's the first stage visual cortex for V1. It goes all the way here via intermediate stage called LGN. Okay, this is another diagram from the left and right eye. It goes to LGN, then finally go to the visual cortex. At this stage, LGN, the two eyes, signals from two eyes are not mixed together. However, by the time it reaches cortex, they start to mix. So for instance, here could be a V1 neuron. It can receive input originally coming from the left eye and from the right eye. And so therefore we can ask, assuming if these inputs are weighted and before it's summed together, what are these weights? Is this weights here heavier than that or so? Experimentally, you can measure these weights, and when you measure them, you can visualize the measuring result. And so ocular dominance column is one of these measuring results, where you get the cortex, you spread out the cortical sheets, you find some neurons weight the left eye input more heavily, and these neurons are clustering together. You can visualize them, let's say, by these black regions to visualize them. It's not really black, it's just staining to make it look black as a visualization. And other neurons may be weighting the right eye inputs more heavily and in white, and they also cluster together. So that's why these are called columns. And these are experimentally measured numbers. You can then ask whether we can understand these weights or the ocular dominance measures from efficient coding principles. This is how one can formulate it. The input signals are seen as two-dimensional and two-dimensional vector rather than n-dimensional in the general case. Here's two-dimensional with one component from the left eye input, the other component from the right eye input. Similarly, we have the input noise. This means that we are ignoring the spatial structure of the input images and focusing only on whether the input is coming from the left eye or the right eye. For example, you can view it as if the image location in each eye is already fixed. Let's say it's at a given location in the left eye and the same given location in the right eye. Or we can also view in another example as each signal is coming from a local spatial average or global spatial average in one eye, similarly for the other eye. So in any case, we are ignoring the exact image location or spatial structure of the visual input, except for from which eye it comes from, left or right, this signal. Then let's take the case that inputs from the two eyes end up on two V1 neurons with O1 and O2 as the net outputs from the retina to these neurons. The encoding matrix K is then a 2x2 matrix. It transforms the two-dimensional retina signals, signal plus noise, to two-dimensional output signals, O1 and O2, by this matrix. so that for each neuron I equal to 1 or 2, let's say I equal to 1 for example, it receives input from both the left eye source and the right eye source. And the weights from each source can be described by K1L from the left eye source, describing this effective neural connection from the retina to the cortical neuron, and the weight from the right eye source. The inputs from the two eyes are correlated. We can describe this correlation by the 2x2 correlation matrix here called RS. So here the top left element is the self-correlation between the left eye input to itself, and so is also from a self-correlation in the right eye input, and the off-diagonal elements are the cross-correlation between the left and right eye inputs. So here, if the two eyes have the same input power, then this 2x2 matrix can be simplified or normalized to this matrix, so that this is the average is the power in each of the eyes, assumed to be equal, and the off-diagonal element R is the correlation coefficient between the inputs from the two eyes. Given these correlations between the eyes, the first conceptual step of the efficient coding is to decorrelate with this K0 matrix. This turns out to be transforming the inputs as left and as right to two new input variables, as plus and as minus. One is the summation signal, summing inputs from the two eyes. The other is the difference signal, subtracting the inputs from the left eye to the right eye. And the summation signal has a larger input power naturally, since the inputs from the two eyes are correlated, so when you sum it up, it's stronger. And this input power is corresponding to the first eigenvalue of the correlation matrix. And difference channel signal has a weaker power for the same reason, because you are subtracting two correlated signals from each other, and this power, input power, is corresponding to the other eigenvalue. These signal powers are the signal to provides the signal to noise ratios to this formula to calculate the gain needed to gain control each of the channels. And so this is for the summation channel, and this is for the difference channel. Then we end up having this encoding transform K composed of decorrelation K0, K0, gain control G, and multiplexing U. And K0 is a 45-degree rotation in the two-dimensional signal space. And G is gain control to each of the decorrelated channels, with the gain described by this formula. And the multiplexing U is another rotation in the two-dimensional signal space to finalize our encoding transform, which is a 2x2 matrix. This gives a quick gist of what binocular efficient coding is. Next, we will dissect each of these steps in detail.